All right, good evening. This is Math 2414. It's January 31st. A couple of announcements here at the beginning. Homework. You turned in homework this last Sunday, January 28th. I will start posting solutions to the homework problems that you're turning in. I will start posting tomorrow, and I will put those in the folder at the bottom of your Google site that's titled Syllabi and Other Documents. So wherever you find the syllabus down there at the very bottom, I'll also put the solutions to the homework problems. And I'll just put them in there identified by date. I think, maybe your section number. I'm not really sure which one, but you'll find them down there. Your next homework, and I'll give you the homework problems that are due at the end of the video, or at the end of lecture, but your next homework will be due February the 4th. Which is Sunday. And remember, every Sunday you'll have, except for test weeks, you'll have homework due. The Exam 1 review is posted. And so let me kind of highlight that because that's a big deal. And I posted that yesterday. And so that's definitely something that you'll want to be looking at over the next few days and start preparing for taking Exam 1. The testing window is February the 8th through the 13th. And you need to take the test, unless you've worked it out with me ahead of time, you need to take the test in a testing center in the Lone Star system. So start thinking about where you're going to be taking the test. And I think we talked about that in the last lecture. On campus hours, I'll be on campus February the 7th and February the 8th next week. On the 7th, I'll be in my office from 4 to 7, and on the 8th, I'll be in my office from 9 to 11. The office number is Winship 115K. All right, and so, which is on the North Harris campus, and so I will always be like the 2 days before each exam window, I'll be on campus. Online office hours, one thing I definitely want to mention, I'm going to change my Sunday hours because of the Super Bowl and giving everybody who is interested the opportunity to watch the game, but also if they need to talk to me on Sunday during office hours. So I'm not going to have any evening office hours on Sunday this week. Instead, this Sunday, they will be from 12 to 1. So most Sundays I'm in my office from 8:30 to 9:30. This Sunday, it'll be from 12 to 1. So everybody can watch the game if they want to, but still come by and ask questions. And then I have regular online office hours next week also. Also remember, during testing windows, I will not have live lecture. So no live lecture next Wednesday, February the 7th, because I'll be on campus that day. And no live lecture the following Monday. So the Wednesday and Monday during that testing window, I will not have live lecture. Okay, so today we are talking about moments and what a first moment is with respect to the x-axis and y-axis in particular, and we're also going to look at center of mass problems. So, and this will be our last, sort of our last application for integration for a little bit, and then we're going to turn our attention to some other things. So. All right, so let's write some things down here about moments and then go from there. So when we're talking about moments, first of all, the first moment is defined to be basically mass times distance. And this is also directed distance right here. So distance has a sign to it, right? It could be plus or minus. And you'll get an idea of what we're talking about as we go through that. So moment is actually a directed quantity. And so the first moment is actually, if you're thinking about it in terms of the way a physics students would think of it, this is actually a vector quantity because it has both magnitude and direction. And so it's considered a vector quantity. The second moment, by the way, and I didn't write that down here, the second moment of a mass system actually goes by a different name. It's called the moment of inertia. And the moment of inertia is not a signed quantity. The moment of inertia is not a vector quantity. It's always positive. Now, what do those moments give you? The first moment is a measure, basically, of the tendency for a system to rotate around a point or a line. And it could actually also be a plane. We're just not going to look at that. That would be a Cal 3 question. So it would be the tendency to want to rotate around a point. So for example, now I've got some information written here about two-dimensional systems. Actually, let me move this down a little bit. And let's briefly talk about one-dimensional systems. So in a one-dimensional system, that would be something we might see on a number line. And so if you have the origin right here at 0, and you have a mass, and we're going to not we're not going to concern ourselves, to be honest with you, too much with the units on mass here. And so I just want to make sure that you know that, and I'll talk a little bit more about mass later. So, I'm just going to assign numbers to these masses, but I'm not going to really put units on these at all. So if I put a mass right here of magnitude 3, and actually let's put the 3 above there, and that mass is located at 2 on the number line. A couple of things here. So first of all, the moment here around the origin, and the moment around the origin is written as capital M sub 0. And the moment around the origin in this case would be the mass times the distance from the origin would be 6. And if you think about it, if you put your pencil or a finger right here and balanced the number line at 0 on your finger, right? Then what would happen if I had a mass there at the point 2, and the mass was size 3, that was its magnitude, the system would want to rotate around that way, wouldn't it? It would rotate clockwise around the origin like that, right? And if I had a mass like this, if this was 0, and I had, let's see, this is 1, 2, 3, 4, -1, -2, -3, -4, like that. And I had a mass sitting here at -3, and its size was 5, like that. Now the moment around 0, around the origin, would be the mass times the distance, and so that would be 5 times -3, or -15. And notice you get a sign to that moment. And what's happening here, this system, if you put your pencil or your finger or something right here at the origin, that system would have a tendency to want to rotate this way, wouldn't it? It would be counterclockwise. So this one would rotate clockwise. Around the origin, around 0. This one would rotate counterclockwise. Around 0. Right, and so this is kind of what we're talking about as far as a little bit, as far as what a moment, what that actually gives you about a system like this. Let me see, let me move this down still a little bit further. Right, so the center of mass for a system, and let's look at it in terms of a one-dimensional system right now. The center of mass is where the system balances. Right, so you can add moments together. So if we had 0 right here at the origin there, and you had, let's say 1, 2, 3, 4 that way, and -1, -2, -3, -4 this way, and you had a couple of point masses there. You know, and when I say a point mass, there's not really any such thing as a point mass, right? This is a highly idealized system that we're talking about. Well, let's say that these are my masses right here, right? And we were trying to find where this particular system balanced, right? We might be trying to find what we call the center of mass of the system. Let me move this down a little bit here. So first of all, the center of mass is, you could think of the center of mass notation-wise, by the way, it's referred to as x bar. And the center of mass is like the place where if you concentrated all the mass at that point, the total mass at that point, it would be equivalent to this point mass system that I have right here with 4 point masses. So that's what the center of mass is. It would be, our point mass system would be equivalent to the system where we took all these masses and simply concentrated them at that center of mass. That would be what we'd call the balance point. All right, so if you think about this for a second, then what would you have here? That the total mass for the system, let's say that we refer to that as M, and let's say that this 5 is, we'll call that mass 1, 6 we'll call mass 2, 4 we'll call mass 3, and 10 we'll call mass 4, like that. So the total mass of the system would be M, and M would just be M1 plus M2 plus M3 plus M4, like that. And what would we have here? We would have that the center of mass is at x bar, remember. We would have that the total mass times x bar, right? Right there, that would give us the moment around the origin. Right, and so notice, right, because you're talking about concentrating all these masses at the center of mass, which is located at x bar. All right, and so if you took the total mass m and multiplied it by the distance, which would be the center of mass x bar, that would give us the moment around the origin. And so notice we come up with a simple way to find the center of mass, and that's just to take the moment around the origin and divide it by the total mass. Right, and so that's how we can calculate where the center of mass is. We first find the total moment around the origin, which would just be 5 times -3 plus 6 times -1 plus 4 times 2 plus finally 10 times 4. And notice what I'm doing there is I'm actually just calculating the moment for each individual point mass. Right, so the total moment around the origin would be -15 minus 6 plus 8 plus 40. And so let's see, that would be -21 plus 8 would be -13 plus 40 would be 27. So the moment around the origin is 27. And then the total mass is simply 5 plus 6 plus 4 plus 10. And so that's 25. And so in this particular case, the x bar here would simply be 27, right? It'd be the total, it'd be the moment around the origin divided by the total mass, so it'd be 27 25ths. So what we're saying is 27 25ths, which on my number line is located maybe right about in here, just a little bit past 1. That's the balance point for this system. That's x bar equals 27 25ths, and that's the balance point for the system. Right, if I put my finger right there, it would balance. And what's the reason why it would balance there would shift over in the positive direction is because I have a very large mass of magnitude 10 that's sitting there at the point 4. And so that is kind of shifting the center of mass in that direction. Okay, so that's a one-dimensional system. If we go into a two-dimensional system with point masses, then now we're talking about two different moments. We're talking about the moment around the x-axis and the moment around the y-axis. So if you kind of look at it this way, let me flip the screen here, and I actually kind of need to add a couple of pages in here probably. So let me go ahead and shift a page in here. All right, so let's go to that page here. So if you took the coordinate plane, I'm going to try to draw this out. And so this is a piece of the coordinate plane like this, right? And on that coordinate plane, we have the x-axis and the y-axis. So let's say that this is the y-axis like this. And then here we have the x-axis. I'll put that one in blue. Right, so there's the x-axis and there's the x-axis like that. Here's x and here's y. So what happens is if you could grip the x-axis with your hands, right, then where that plane has a tendency to rotate around that x-axis. So you're literally, let's see if I can draw this so that you won't laugh. Let's say that here you are. This is a person right here, right? Very skinny person. But they are holding the x-axis with their hands. And instead of an arrow, let me put hands here. So that person is holding the x-axis with their hands. And this person looks pretty badly deformed here, right? Very skinny arms. They look like they're from Mars or something. But they're holding on to that x-axis. So what's going to happen when they hold on to that x-axis on both of those sides, this system, depending on where these point masses are, this system is either going to have a tendency to want to rotate around the x-axis this way, with this part of the y-axis coming up and this part going down like that. Or what's going to happen, I'll do this in a different color, the system would want to rotate this way, where this part of the y-axis is going down and this part of the y-axis is going up. Right, so one way or another, you're going to get some kind of a rotation probably around that x-axis. And the moment around the x-axis measures the tendency of the system to want to rotate around that axis, right? So I don't know if that's a good drawing or not, but so m sub x is the moment around the x-axis. And this measures the tendency of the mass system to want to rotate around the x-axis. Right? And the, pretty horrible drawing, I definitely understand that. But hopefully that will give you some sense of what we're talking about here physically. And so the moment around the x-axis is simply the point mass, and I want you to think about now with the, if we're talking about around the x-axis, if you have a point mass sitting out here, let's say, and that's m1 right there, then what measures the distance that mass is away from the x-axis? Well, that would be the y-coordinate of that point. If that point is located at x1, y1, then the y-coordinate of that point actually measures how far it is away from the x-axis. And so the moment around the x-axis would be m1, y1 plus m2, y2, and however many point masses there are. And in the same way, exactly the same way, the moment around the y-axis would just be m1 times x1 plus m2 times x2 plus and so on, right? And so those moments are, you have to use the distances away from the axes. And what gives you the distance away from the x-axis is the y-coordinate of the point. And what gives you the distance away from the y-axis? It's the x-coordinate of the point. Okay, so with that in mind then, I'm still not ready for that picture yet. So let's bring in another page here, okay? So we've talked about a one-dimensional system, so let's look at the two-dimensional system now. So if you, where we have point masses sitting on the plane now, right? So the center of mass for this system is going to be located at the ordered pair x bar, y bar, right? That's called the center of mass for the system. That's the notation we use. And remember now, the total mass for the system is m. And remember, the center of mass is the point where it would be equivalent to take all of the mass and locate it at that center of mass. That would be an equivalent mass system. So what do we have here? That the moment around the x-axis is simply the total mass times the distance that the center of mass is away from the x-axis, which would be given by y bar. And the moment around the y-axis would be the total mass times the distance that that mass is away from the y-axis, which would be given by x bar, like that. And so what we have, remember what we're trying to do is come up with ways to find that center of mass. And so x bar would be equal to the moment around the y-axis divided by total mass. Y bar would be the total moment around the x-axis divided by the total mass. All right, so a couple things to draw out here, or to put in boxes. First of all, the center of mass is x bar, y bar. One thing we wanted to definitely identify. Total mass is simply the sum of all the masses, and so that's m. And then finally, we have that the center of mass of the system could be found by taking the moments and dividing them by the total masses. So far, notice, by the way, absolutely no calculus in any of this, right? And we're getting there. All right, so let's say that we have mass 1, right? And that's equal to, has a magnitude of 5. Here's mass 2. That has a magnitude of 10. Here's mass 3. Has a magnitude of 8. And then finally, let's say that here's mass 4, and it has a magnitude of 20. It's much bigger than any of the other ones. Right? And so we want to find the center of mass for the system, the balance point for this system. All right, so find the center of mass for this system right here. Okay, so what do we have here? That we calculate the moments and the total mass. So the total mass is simply 20 plus 8 plus 5 plus 10, right? Just add all the masses together. And so that gives you 43. And then we look at the moment around the x-axis and calculate that. And so the moment around the x-axis, you take each one of the masses and you multiply it by its distance from the x-axis. So let me kind of put those lightly here. So for, let's start with M1. M1 is distance from the x-axis is the y-coordinate, right, of that point. Now let me write those coordinates down here. This point's at 3, 2. This point is at 5, negative 2. M3 is at -2, -2. And finally, M4 is at, let's see, -4, 5, like that. All right, so let's go through now and look at each one of those masses. For the total moment around the x-axis for M1, you have the mass, which is 5, times its distance from the x-axis, and that would be that y-coordinate at that point. That would be 2. So it would be 5 times 2. Plus M2, the moment around of that second mass would be 10 times its distance from the x-axis, which is this distance. It's the y-coordinate, so it would be -2. Plus, and then for M3, you have the total mass, which is 8 times its distance from the x-axis, which would be -2 also. And then finally, this last point, M4, its mass is 20 times its distance, which is 5, right? And so you get, what, 10 minus 20 minus 16 plus 100 there. And so what do you get there? You get 10 minus 20 is -10, minus 16 would be -26, plus 100 would be 74. So that's the total moment around the x-axis. It's positive because, especially because of that mass of at 4 right there, its magnitude is 20. It's such a large mass that it's really making the system want to rotate in that direction around the x-axis. And then the moment around the y-axis, you're doing exactly the same thing now, except now you're looking at distances to the y-axis. So for M1, what do you have there? You have a distance of, where you have a mass of 5 times a distance of 3 at the x-coordinate at that point now, plus M2, mass is 10 times its distance from the y-axis, which would be 5, plus M3, the mass magnitude is 8 times its distance from the y-axis, which would be -2. Notice those are all x-coordinates now. And then finally, plus the last one for 4, that mass is 20. Its distance from the y-axis would be -4, the x-coordinate at that point. All right, so what do we get there? That'd be 15 plus 50 minus 16 minus 80. So you have 65 minus 16 be 49. 49 minus 81 is -31. All right, so you've got the two moments calculated, the moment around the x-axis and the moment around the y-axis. So what do we have in our problem here? We have that x bar is the moment around the y-axis divided by total mass. So it'd be -31 divided by 43, about -3/4. And y bar would be the moment around the x-axis divided by the total mass. And so that would be 74 divided by 43. Right, so that would be like 1 3/4. And that would be our center of mass. It would be located at that point. -31 43, 31 43rds, and then 74 over 43, like that. So the total, the center of mass would be somewhere in this vicinity where I'm putting this black dot in there. It would be kind of sort of where that center of mass is located. Right, notice it's skewed off towards that massive magnitude 20 because that one's so much bigger than all the other ones. So that would make sense too. All right, still this is not a calculus question here at all. We're still not ready to do that yet. So our next stop here. Okay, so now we're finally ready for this picture. So now let's, instead of looking at point masses, let's look at what we call thin plates right here. These thin plates are sometimes called lamina. And these plates are so thin that what we do is we essentially kind of ignore the thickness of the plates altogether, and we look at the density as being the mass per square per area, right? So the density, we usually use the Greek letter rho, which is kind of a script P right there. And script P, that is simply the mass per area. So per area would mean like mass per square inch per square foot, right? And that, again, do you have plates that are actually like this? No, this is a highly idealized system. These kinds of plates don't exist, but it does approximate problems where you do get these thin sheets of metal, things like that. You certainly have to pay attention to thickness when you're talking about the density, but here we can kind of sort of, if it's uniform density, which we're going to assume, right? We're going to assume uniform density. So if you assume uniform density, then you could just look upon this as density per, or be mass per area. Now, lots of objects where the object is not uniformly dense. So just look like, for example, at the Earth. The Earth is certainly not uniformly dense. As you get closer and closer to the center of the Earth, it becomes more and more dense. The same with the Sun. Objects like that, they become more and more dense typically as you get closer and closer to the center of the object because of the forces of gravity. All right, so what we're going to do here is we're going to find the center of mass for this system. So I've got the exact same object drawn twice here. So we're going to assume here that that this particular object has uniform density, right? And so the total mass at any particular object like this would simply be rho times area, right? Density times area. That would be the total mass there. All right, so let's look at this particular object here, in that if I could take it now and divide it into pieces, so like if I divide this into a green piece that's a nice rectangle, right? The original piece, the original thin plate was not a nice little rectangle. So I'll put that green piece there, and that's a nice little rectangle like that. And then let's say I make this piece right here. It's kind of purplish pinkish color that I'm using right here. We'll divide that piece up. That's also a nice rectangle. Right. So what are we doing here? We're taking this irregular looking plate and we're dividing it up into several pieces that are very regular in shape. And then finally, we'll do this last piece, same thing. The thing is, if these things are all uniformly dense, then their centers of mass for each of those individual pieces are easy to calculate, easy to locate, right? It's just the center of where the object is. So, for example, this green piece, its center of mass would be located at that first point. That would be the center of mass right there of the green piece. Right, and we're simply doing the same thing for all of these, right? So this point right here would be the center of mass of the purple piece. I guess it looks more purple than pink, so I'll say purple piece. And that would be that point right there. And then finally, this piece, this dot right here would be the center of mass of the brown piece. Like that. So what can we do? We can take the, those are nice little rectangles. So the area of the green piece, is simply just 2 times 3, or 6, like that. Right, and so the mass of the green piece then is simply going to be 6 times rho. Right, so its total mass is going to be 6 times rho. rho times 6, right? It's the density times the area. The purple piece, its mass, well, let's see, the area of that purple piece it's 8 units wide, 2 units tall, so its area is 16. So the total mass there would be 16 rho. And then finally, the brown piece, its total mass would be, let's see, its area would be 4 times 2 would be 8, so that'd be 8 rho, like that. All right, so what are we saying? We're saying that we take this plate, we divide it up into nice regular pieces, and these regular pieces we can identify the center of mass. So what we've done is reduce this irregular plate to these 3 point masses right here. And we know what their masses are, 6 rho, 8 rho, and 16 rho here. And then we can calculate the center of mass here, because we can now do the moments, right? The moment around the x-axis would simply be, let's see, and I should probably write the coordinates for each of those points down here also. So in the green, 1, 2, 3, 1, 2, 3. So the coordinates of that piece, of that center of mass are at 3, 3. 1, 2, let me make sure I count it right. Actually, not 3, 3. 1, 2, 3, 7 halves, sorry. So let me back up here. That point is located at 3, 7 halves. Okay, the purple piece, its center of mass is going to be at 0, 1. That one's easier. And then finally, the brown piece, its center of mass is going to be located at 2, negative 1. Like that. So what are we going to have here? That the moment around the x-axis is going to be, if we go around and look at each one of those, is going to be 6 rho. Remember, we're talking about around the x-axis, so this would be 6 rho times 7 halves, right? Because it's the distance from the x-axis, plus, and then the purple piece would be 16 rho times 1. And then finally, the brown piece, its total mass is 8 rho, and that would be times negative 1. Right, so let's see. So you have 21 rho plus 16 rho is 37 rho, minus 8 rho would be 29 rho. That would be our moment around the x-axis. So a moment around the x-axis would be 29 rho. All right, and then the moment around the y-axis, I know this is kind of tedious work here, and we're gradually heading towards looking at calculus problems, believe it or not, here. So the moment around the y-axis, we'll do this in the same order, so we start with the green piece. So this is going to be 6 rho times 3. And then the purple piece would be 16 rho times 0. So notice that purple piece is symmetric around the y-axis, so it makes sense that its moment around the y-axis would be 0. That it would cause no rotation around the y-axis. And then finally, the brown piece, its mass would be 8 rho times the distance from the y-axis, which would be 2. And so the moment around the y-axis would be 18 rho plus 0 plus 16 rho, be 34 rho. All right, and then we have the total mass of the system. Finally, the total mass of the system is simply 6 rho plus 16 rho plus 8 rho, or 30 rho. And so what do we have here is that the x bar is going to be the moment around the y-axis, 34 rho, divided by 30 rho. Notice the rows cancel. It's one reason why I did all this. And so you have 17/15ths as the x-coordinate of the center of mass. And then y bar would be 29 rho divided by 30 rho. And so that'd be 29/30ths. Again, the rows divide out. So the center of mass, the x-coordinate, is just a little bit past 1. and the y-coordinate is just a little bit less than 1. So the center of mass, if we go back to the original picture, is somewhere right about in there. That's x bar, y bar. And that's presumably for this uniformly dense thin plate where it would balance. If you put your finger underneath that point right there, it would balance at that point. There'd be no rotation in either around the x-axis or the y-axis. All right, so we've got these nice regular figures, and so the deal is, how do you do this if you don't have nice regular figures? Also, the other thing to notice in this picture, in this problem, is that the density, if it's a uniformly dense object, then the density really doesn't have anything to do with where the center of mass is. It just has to do with the area. So notice that for a uniformly dense thin plate, we can neglect density because it's going to drop out. We can neglect density to calculate x bar, y bar, right? Because it's not going to affect it. All that's going to affect it is the distance, basically, from the axis that you're talking about and the area. All right, so if we write down the moment, then, is mass times distance. But if we can neglect density, then mass is really equivalent. And for these thin plates, for a thin plate, we neglect density. And so we get that the moment then is simply area times distance. Right? And so remember, it's got to be uniformly dense, thin plate, right? Those things have to be what we're talking about. So what we do is we take, so if we have this region up here in my picture, and we're trying to find the center of mass for this plate that is bounded by these two curves. So this is the uniformly dense thin plate, right, like that. So this is the uniformly dense thin plate, and we call that sometimes a lamina, right? Then what we're doing is we're breaking it up into a bunch of rectangles, and we're finding essentially the moments or the centers of mass for each one of these rectangles, which is just the center of the rectangle, like that. And so then we can calculate the moment around the x-axis and the y-axis, because it's like we can think about concentrating that rectangle in that one point. So for example, so I separate one rectangle out here so that we can kind of look at it more carefully. So there is the center of mass for that particular green rectangle. And how far is that away from the x-axis? Well, that would be given by the y-coordinate there, right? And but instead of saying the y-coordinate there, what would we do? It's the point that's halfway between the two curves. And so we can say that that is simply the f of x plus g of x divided by 2. And that's that distance, because that's exactly halfway between the two curves. And how do you find a point that's halfway between two things? You add them together and divide by 2. And then how far is that point away from the y-axis? Well, away from the y-axis, it's exactly x units away. So that's the distance that rectangle is away from the center of mass of that rectangle is away from each of the axes there. So what do we have here? That we can start writing some things down and generally head towards the integrals that we use for these kinds of problems. So the area of the rectangle, which is equivalent to mass, remember, the area of the rectangle, and I'm going to put in parentheses that that's equivalent to mass here, that is going to be given by, well, that goes back to what we did a couple of days ago in class, and that is you simply take the two functions and subtract them, right? It's upper curve minus lower curve, and then dx, right? That's height, length times width for the rectangle. And then the moment around the x-axis would just be the area of that rectangle, right? Because remember, moment would be mass times distance, or area times distance. So I've got the area piece there. And what's the distance from the x-axis? Well, it would be f of x plus g of x divided by 2. So it's f of x plus g of x divided by 2 times area. Like that, right? And so what do we have here? This is distance right here from the x-axis. This is area. And remember, area is equivalent to mass for these thin plates. And then the moment around the y-axis would simply be the distance from the y-axis, which is given by x, and that would be times area. F of x minus g of x dx, like that. And again, what would x represent? It represents distance. And what does f of x minus g of x dx represent? It represents area. And so we've written down the quantities here that are going to give us the quantities that we need here. The other thing we need, by the way, is, oh yeah, we already have the mass written down there. So we've already got that done. Okay. So then I can use just, or make the jump to integrals to write these quantities out. So what I'm going to do here is I'm going to copy these quantities down here and paste them into the next page so we have them there. So copy that, go to the next page, I'm going to paste it. Like that. And so we come up with these quantities, that the total mass for the system is simply the same as area. And so that's going to be equal to the integral from a to b of f of x minus g of x. In other words, our very familiar upper curve minus lower curve. And then the moment around the x-axis is going to be the integral from a to b. And now, by the way, I want you to notice that as I'm writing these integrals out for the moment around the x-axis and the y-axis, that what's going to happen, that area piece is going to occur in both of these integrals. So once you have that area piece written down, then you know it's going to appear in these two integrals also, like that. And then what it's going to be multiplied by in each case, it's going to be multiplied by distance. So for the moment around the x-axis, you're going to have f of x plus g of x divided by 2 is our distance. And for the moment around the y-axis, this is going to be much easier. It's just going to be x. Right? And then remember, what do we know? That the center of mass for the system is simply x bar is moment around the y-axis divided by total mass. Y bar is moment around the x-axis divided by total mass. All right, so that gives us a way to deal with these kinds of problems. All right, and so now we're gonna kind of put a box around this material right here. This is what's driving what we're doing here. And so then we're going to tackle some problems. All right, and then that's how we'll finish up class today, just to tackle some problems. So now let's look at some problems where they actually use calculus to solve the problem. So let's say we have this function, f of x equals 9 minus x squared. And I'm looking at the region that's bounded by 9 minus x squared and y equals 0. And I want to find the center of mass for this plate. Find the center of mass for this thin plate. All right, so let's first get a nice little picture of what this looks like. Always a good idea to do that, so you can make sure you know that what you're doing is making sense, certainly. So 9 minus x squared, you know, is a parabola 1, 2, 3, 4, 5, 6, 7, 8, 9. Has a vertex up here at 0, 9, and then goes through 1, 8, negative 1, 8, and 2, 5, negative 2, 5, finally 3, 0, negative 3, 0, like that. So we've got this parabola, right, that defines this very thin laminar plate, like that. All right, so this is the plate we're talking about. And we want to find the center of mass. We want to find the balance point for the center of mass. Now, one thing right away that you notice here, and I want to talk about this as we go through the problem later on, is that notice that the object is symmetric around the y-axis. Object is symmetric around the y-axis. So what does that mean? That tells you that x bar, the x coordinate of the center of mass, has got to be 0. And remember, what is x bar equal to? X bar is equal to the moment around the y-axis divided by the total mass. And so if x bar is equal to 0, that tells you that the moment around the y-axis has got to be 0 by symmetry. Right? And I will allow you to do that if you can see that symmetry is coming into play in a problem you're dealing with. If you can identify that, then you can tell me that a particular moment is equal to 0. That's okay. Now we're actually going to show that it's equal to 0 on this particular problem, but I wouldn't necessarily ask you to do that. So, all right, so if we want to find the center of mass, what do we need to do here? We need to write down 3 integrals. We need to write down the mass integral. And remember, mass integral in this context is simply the same thing as area. And so that would be the integral from negative 3 to 3 of just 9 minus x squared dx. Super simple integral. I'm not going to be going crazy here on nasty integrals or anything like that. All right, well, that area is certainly symmetric around the y-axis, so I always like to get 0 as a limit of integration. So I multiply by 2 and I go from 0 to 3 and integrate like that instead. And so the antiderivative here would be 9x minus 1/3 x cubed. That goes from 0 to 3. And so what you end up with there is 36 when you do that arithmetic. Right, substituting in 3, and the lower limit of 0 just gives you 0, obviously. So the area of that region, or the total mass, would be 36. All right, the moment around the x-axis, and by the way, for finding area, dividing up a region into 2 symmetric pieces and then just multiplying by 2 is a legitimate way to find that area. All right, now the moment around the x-axis, you know, if you're going to look at a nice little representative rectangle in here, so let's say we've got this rectangle like this. Not a bad idea to draw in this rectangle like this. And then look at the center of that rectangle, and you're talking about how far the center of that rectangle is away from the 2 axes. So you've got that distance there, which is given by x, and this distance this way, which is, remember, in this case, you're not adding 2 functions together, you're just adding 1 function and dividing by 2. So this would be y divided by 2, or 9 minus x squared divided by 2. Technically, it's 9 minus x squared plus 0. All right, so what's the moment around the x-axis going to be here? The moment around the x-axis is going to be the integral from negative 3 to 3 of the distance that rectangle is away from the x-axis. So that'd be 9 minus x squared over 2 times the area piece, and that was the piece that I had in my first integral, which is 9 minus x squared dx. So don't forget here that this little piece right here to the integral is area, and this piece right here is distance, and it's distance from the x-axis. Right? All right, so what do you end up with there? You could, since both of these pieces are on the same side of the x-axis, they're both above the x-axis, I would be allowed in this problem once again, to make my life a little bit easier by multiplying by 2 and going from 0 to 3. And then if I take that 2, this 2, outside of the integral, that will end up canceling with the 2 that I'm multiplying by to double the region, essentially. So let's see, I'm going from 0 to 3, and this is going to be 81 minus 18 x squared plus x to the 4th dx. And so the moment around the x-axis is going to be 81x minus 6x cubed plus 1/5 x to the 5th. And that's going to go from 0 to 3. And when you put 3 in there, you get a little bit of messy arithmetic. You do get 243 minus 162 plus 243 over 5. And that ends up, when you add all that together, you end up with 648 over 5. I just did the arithmetic ahead of time. And so there's our moment around the x-axis. All right, and then finally the moment around the y-axis is going to be the integral from -3 to 3. And then remember, the area piece is sitting in here already. This is area right here. And then distance is this piece right here, and that would be x. Remember, it's distance times area. Now, remember, what's supposed to happen here? What's supposed to happen is you should get 0 by symmetry. Now, so this is equal to 0 by symmetry. Now, if you have the region and multiply by 2, like I did on the moment around the x-axis, around the area, you won't get 0. And the reason why you don't get 0 is because these pieces are on opposite sides of the y-axis, and so the moments of those two symmetric pieces have opposite signs. And so if you divided that region up and multiplied by 2, you would not get 0. So you have to be really careful. The only time you can divide the region up and multiply by 2 is when you're looking for area, or if all the pieces to that region are all on the same side of the axis. But if they're on symmetric sides, if you have symmetric pieces on opposite sides of the axis, you cannot divide it up into 2 pieces and multiply by 2. So this is something a little bit that you got to be careful about. And so then finally, what are we doing? Remember what the whole purpose of this is, to get the center of mass for the system. And so the center of mass for the system, we know that x bar is equal to 0. So let me go ahead and write this at the very top here. So x bar we know is equal to 0. Y bar would be the moment around the x-axis, which would be 648 over 5, divided by the total mass, which would be 36. And so you get 648 over 180. And then whatever that is, let's see, let me get my calculator out here and get a decimal for that. So you have 648 divided by 180. 648 divided by 180 is about 3.6. Not about 3.6, it is 3.6. And so 3.6 is that's where the center of mass is located, right about in there. Right, that's x bar, y bar right there. And in that picture, that certainly would make sense. That seems to make sense there, and it certainly fits the picture pretty well. All right, so that's a good center of mass problem. Let's look at another center of mass problem where, and this will actually probably be the last problem we'll look at for center of mass, at least for now in class. So that's good. This is going to be maybe a little bit shorter of a lecture than the previous one. So let's say we have x equals y plus 2 and x equals y squared. All right. So x equals y plus 2 we know is a linear function. And if you're concerned, you'd certainly want to know where these two intersect. So you'd set y squared equal to y plus 2. You'd have y squared minus y minus 2 equals 0. And so that would give you 2 and negative 1 as points of y coordinates of points of intersection. And then x would be equal to, x is y plus 2, remember. And so x would be 4 here, and you get a point of intersection at 4, 2. And then for x equals y plus 2 on this one, you get x equals 1. And so you'd get a point of intersection at 1, negative 1. So you have a point of intersection at 1, negative 1, and another one at 4, 2. Right? You've got this line that looks like that. So that's x equals y plus 2. And then you have our parabola that opens to the side, goes through 0, 0 certainly, and then 1, 1, and negative 1, 1. And so you've got this parabola that looks like this. All right, so what we're trying to do is find the center of mass for that piece right in there. Now, because x is written as functions of y in both of these problems, this is a problem where we would have to do everything with respect to y rather than with respect to x. You know, we use a horizontal rectangle here, and that would be the center of the rectangle right there. And so this one's going to be backwards from what the problems I was just doing as far as writing out all the integrals here. And remember, there's going to be 3 integrals to write out in this problem. So first of all, the mass piece is, remember, just the integral for area. And in this context, it would be the integral from negative 1 to 2 of right curve minus left curve. It'd be y plus 2 minus y squared dy, like that. Right, and so area would be, just clean that up ever so slightly, would be negative y squared plus y plus 2 dy. Now we can calculate that, you know, in a minute, but and in fact maybe we should just go ahead and calculate that now. So that's going to be equal to negative 1/3 y cubed plus 1/2 y squared plus 2y. That goes from negative 1 to 1. There's no symmetry with this region, so I can't split up a region and divide by 2 or anything. And then you put 1 in there, and in the upper limit, you have negative 1/3 plus 1/2 plus 2. Minus the lower limit, you put negative 1 in. Now, negative 1 cubed is negative 1 times negative 1/3 is positive 1/3 plus 1/2 minus 2. Kind of yucky arithmetic at the end, but it's not horrible. So you end up with negative 1/3 plus 1/2 plus 2 minus 1/3 minus 1/2 plus 2. Now let's see, the 1/2s go away, and 2 plus 2 is 4, and then you have 4 minus 2/3. So you get 12/3 minus 2/3, so that's 10/3. And so that would be the area. So that's our mass up there. Mass would be, remember, it's the same thing as the area. It's going to be 10/3. And then we look at the moment around the x-axis. So when you write that integral out, the limits of integration are going to be the same. And then remember, one part to this integral is the mass piece that we just wrote down. So this would be negative y squared plus y plus 2. So always remember that once you've got this integral set up for the mass, that piece occurs in the other 2 integrals. And now this has got to be the distance from the x-axis. And so the distance from the x-axis is this distance in my picture. And that's simply just given by the y-coordinate. And so that's our integral for the moment around the x-axis. It'd be the integral from negative 1 to 2 of negative y cubed plus y squared plus 2y dy. And so when you write out that, do that integral there, that would be negative 1/4 y to the 4th plus 1/3 y cubed plus y squared, and that would be from negative 1 to 2. I'm going through that pretty quick because I know all of you know how to do that part of it. So I just want to kind of get to the answer at this point. So, so at the upper limit, you've got, let's see, that's going to be 2 to the 4th power is 16 times negative 1/4 would be negative 4 plus 8/3 plus 4. That's our upper limit. Minus the lower limit. Negative 1 to the 4th power is 1. So you have negative 1/4. And then that would be minus 1/3 and then plus 1. And so that's going to give us negative 4 plus 8/3 plus 4. Those are going to cancel. Plus 1/4 plus 1/3 minus 1. So the 4's go away. And you have 8, oh, that works out nice. 8/3 and 1/3 is 9/3, which is 3. Minus 1 would be 2. So you have 2 plus 1/4, or 2 1/4. So you end up with 9/4 for the moment around the x-axis. So the moment around the x-axis is 9/4. And it better be positive because this region is more of the region is above the x-axis than below. So getting a positive moment around the x-axis makes sense in this picture. If you look at that region that I've shaded at the top, more of it is above, a lot more of it is above the x-axis than below the x-axis. Finally, the moment around the y-axis. These can be long problems because there's 3 integrals involved. Here's the mass piece. You get negative y squared plus y plus 2 dy. But unfortunately, the other part is a little bit more complicated. Let me give myself a little bit more room here. All right, and so notice that's this distance this way from the y-axis. And so what you have to do there is add the 2 functions together and divide by 2. So you actually take y plus 2 plus y squared, add them, and then divide by 2. So this is a yuckier integral here. So you could take the 1/2 outside the integral, and then you've got y squared plus y plus 2 times negative y squared plus y plus 2. So almost the same quantity, not quite the same quantity, but almost the same quantity, dy, like that. And so unfortunately, then what you'd have to do is multiply that out, and then go from there. So I'm probably just going to leave that for you. I'll leave this for you because it's messy multiplication. And but you know how this is going to finish out here. And this quantity better be positive also, because this region lies entirely to the right of the y-axis. So what have I done? I found enough information to get y bar up there. Y bar would be the moment around the x-axis divided by total mass. And so it'd be 9/4 divided by 10/3. And so that would give you 27/40. And so that would be the y-coordinate of the center of mass. More than 1/2, but not quite 1 from what I'm getting there. So, all right, and then x bar, I haven't done the calculations far enough to do that. We just know that that's the moment around the y-axis divided by the total mass, which is 10/3 right there. And so then you finish that. All right. So those are two problems to use as kind of as a guide when you're looking at these kinds of center of mass problems. Let me flip the screen here. So the homework that is due February the 4th by midnight. 2 problems. I've assigned already section 2.4, problem number 176. And now that we've done center of mass, section 2.6, problem number 274. So those 2 problems are due but before the end of the day on Sunday. Make sure that you use the correct name for your file. Almost all of you did a really good job with that. when you turned in your homework. So that was awesome. So, all right. So I hope everybody has a great rest of the week and weekend. Please email me if you have any questions about anything as we're getting prepared for exam 1. We will cover new material next Monday, but that material will not be on exam 1. That'll be on exam 2. So exam 1 stops with what we did today. What we cover next Monday will not be on exam 1. All right. All right. Have a great week.